Hey everybody. Today we're talking about the integral test. This is one of the most powerful tools we have for determining whether infinite series converge or diverge. It goes like this. We're looking at an infinite series, n equals 1 to infinity an, so an is just the generic term of the series. Suppose we have a function that agrees with that series. So that's just a fancy way of saying take out the n's and replace them with x's, have a function f of x. The difference is that that's supposed to be defined for all x values, not just for the positive integers. Now suppose that that function is positive, decreasing, and continuous for x greater than or equal to 1. The integral test says that you should look at the improper integral of that function instead of the infinite series. Integral from 1 to infinity f of x dx. If that converges, so does the series. If that diverges, so does the series. This is nice because we have a lot of techniques of integration at our disposal. We're probably better equipped to handle the integral from 1 to infinity f of x dx than that infinite series. One quick comment, the starting point on the series doesn't matter. You can start at n equals 0, 1, 2, a million, it doesn't matter. Convergence and divergence are determined entirely by what happens to an eventually, not what happens initially. Along the same lines, it's okay if that function f of x doesn't start out positive, continuous, and decreasing, as long as it ends up that way and stays that way eventually. One other thing to recognize, the integral test doesn't tell you anything about the actual sums of the series. So the integral from 1 to infinity f of x dx is not going to be actually equal to that series. They just converge or diverge together. So let's justify the integral test with a picture. Here, the shaded area is representing that series, the sum of the series. Each rectangle has width 1, and each rectangle has height an, so a1, a2, a3, and so on. So that series is going to converge exactly when the shaded area is finite. What about that improper integral, 1 to infinity f of x dx? So f of x is supposed to agree with the series on the integers, so f of 1 is a1, f of 2 is a2, and so on. The improper integral 1 to infinity f of x dx is the area under that graph from 1 to infinity. The integral test says that that area will be finite exactly when the shaded area is finite, which I think is at least intuitively plausible. Let's do a couple of examples. In each case, notice that we have some n's here, 1 over the square root of n plus 4 and ln of n over n cubed, that'll be reasonable to integrate. The integral test requires that we actually integrate functions, and so we need things that we can actually handle. Problem 1. Sum from n equals 1 to infinity, 1 over the square root of n plus 4. So the corresponding function is 1 over the square root of x plus 4. Before we can apply the integral test, we have to check 3 things. Is that function positive? Yes. The square root of x plus 4 is always positive, therefore so is f of x. Is it continuous? Yes. Notice that the sum is going from 1 to infinity, x is greater than or equal to 1 here, so continuity is not an issue. The denominator is never 0. Finally, we need to ask if this function's decreasing. That's not maybe quite as obvious. Fortunately, we have a tool for determining when functions are increasing and decreasing. It's called the derivative. So let's actually differentiate 1 over the square root of x plus 4. Or to say it differently, differentiate x plus 4 to the negative 1/2. We get negative 1/2 x plus 4 to the negative 3/2, which is always negative, because x plus 4 to the negative 3/2 is always positive. Therefore, f of x is always decreasing. That lets us know that we can apply the integral test. We can look at this improper integral. Whenever we do an improper integral, we start by writing a limit. Take out the infinity, put in an r. We'll do that proper integral, and then later take that limit as r goes to infinity. So let's do it. Anti-differentiate. Plug in the endpoints. Now evaluate the limit. As r goes to infinity, 2 times the square root of r plus 4 goes to infinity as well. So this improper integral diverges. Therefore, by the integral test, the series that we started with diverges as well. Problem 2. Sum from n equals 1 to infinity, natural log of n over n cubed. So we're looking at the function natural log of x over x cubed. As before, we need to check the same 3 things. Is it positive? Yes. X has to be greater than 1 here, and therefore the natural log is going to be greater than 0. Obviously, x cubed is going to be greater than 0 always when x is greater than or equal to 1. Is the function continuous? Yes. As long as x is greater than 0, this function is continuous everywhere. Finally, is it decreasing? So again, we need a derivative, and we need to see where the derivative is negative. Quotient rule, low d high minus high d low, draw the line square below, and a little bit of simplification gives us 1 minus 3 natural log of x over x to the 4th. So the function is going to be decreasing where this numerator is negative, 1 minus 3 ln x less than 0. Solving that for x, we get x greater than e to the 1/3, about 1.4. So this function is decreasing when x is greater than about 1.4. So x greater than or equal to 2 does it. Remember, it doesn't matter if the function's decreasing to start, as long as it's eventually decreasing. And that's the case here. The integral test is going to apply. So let's look at the improper integral, 1 to infinity, natural log of x over x cubed dx. We start by putting in a limit, once again, limit r to infinity integral from 1 to r, natural log of x over x cubed. This one's going to require integration by parts. The way I want to do my integration by parts is just by finding an antiderivative and then worrying about the limits of integration only at the very end. So using I-late, I see a log. I know that's a good candidate for my u. So I'm going to take u equal natural log of x, dv equals 1 over x cubed dx. Differentiate the u, anti-differentiate the v, and apply the formula integral of u dv equals uv minus the integral of v du. Keeping the limit in, I will evaluate that later, and keeping the limits of integration as they were. I'll also do those later. I still have one integral left, so let's go ahead and do that. We're going to evaluate the integral of x to the negative 3 dx. So overall, I'm getting that 1/2 of that integral is negative 1/4 x to the negative 2nd. Plug in the r, plug in the 1, simplify it just a tiny bit, and recognize that now I have to do the limit. If that limit is infinite, the integral will diverge, and therefore so will the series. If it's finite, the integral will converge, and so will the series. So it really all comes down to that limit. Unfortunately, it's an infinity over infinity indeterminate form. Now we have to use L'Hopital's rule. So let's do it. Differentiate the top, 2 over r. Differentiate the bottom, 8r. Simplify it a little bit, 1 over 4r squared. In the limit, that's 0. So overall, that tells us that this improper integral converges. And therefore, by the integral test, so does this infinite sum.